To Meta Quest devs, performance is as challenging as it's important. It's challenging because, let's be honest, we have a mobile processor that's in an extremely thermally constrained environment. The device is in users' faces after all. But it's also equally important just because of how many user-facing outcomes that are dependent on that performance. We sometimes have a mantra where we say that on other platforms, frame drops are a bit of a minor inconvenience. No one likes them. But in VR, frame drops can equal nausea. So the stakes are really high, and that's why we at Meta and you as devs are often trying to do everything we can to give you as much of a performance budget as we can. Now, last year, we unveiled the Meta Quest 3, and we were really proud of how much of a performance increase it was over its predecessor, the Quest 2. Specifically, we were able to quote an over 2x GPU win. Now, this year, as you saw from today's keynote, the Meta Quest 3S is the new device, and that has the exact same CPU and GPU budget as that of the Quest 3. So we're not going to get any hardware wins that we can directly share today, and that means that we have to look at software for today's talk. So in today's presentation, we're going to go through just a series of software side wins, really at all layers of the stack, like the OS, graphics drivers, and all the way up to the application layer, Unity and Unreal, where we've been able to unlock some more performance for your apps. So as a quick intro, I'm Neil Bedecker, and I'm a tech lead manager at Meta, whose team is pretty much unilaterally focused on giving your Quest devs and your apps a much larger CPU and GPU budget, as well as better graphics, a better visual quality, a better image. And I'm really excited to be joined by Trevor Dash, our lead software engineer, who, among many things, is the current tech lead for application SpaceWarp. So today, we're really going to just go through a set of CPU and GPU optimizations, as well as visual quality wins that we've been able to make software side to make your Quest apps much better. And here's a little bit of a look into, maybe you could call it our perf optimization framework. It really all starts and begins with GPU, which is sometimes what we think of as the most scarce resource on board the entire device. It's what controls the visual quality rendered. It's what controls how many pixels you can render, what kinds of meshes and shaders that you can even use in your apps. But then CPU is not far behind because of how heavy the CPU workloads of so many of your apps are. Unity main thread, as an example, is notoriously heavy and almost monolithic with how much CPU it consumes. So we're really excited to share one or two optimizations on the CPU side. And finally, visual quality enhancements. We have a bunch to share here, specifically some really core wins in App SpaceWarp, and we're excited to touch upon all three of these today. So with that, I'm happy to hand it off to Trevor, who's going to discuss all of these topics in a lot more detail.
Hi, I'm Trevor Dash. As a software engineer at Meta, I spend most of my time focusing on figuring out ways to improve performance, especially on the GPU, so that you can get the most visual quality possible. We've got a lot to cover today, so we're just going to dive right in. Here's a quick look at what I'm going to talk about. Application SpaceWarp, GPU tile alignment, symmetric projection, and subsampled layout. After that, I'm going to hand it back to Neil. He's going to talk about a couple other GPU, CPU wins that we made, and then at the end, we'll have some time for Q&A. So keep all your questions in mind. So, Application SpaceWarp. Application SpaceWarp is a powerful tool that can dramatically increase your GPU and your CPU headroom. We do this by having the application render at half of the display refresh rate, and then our runtime will synthesize the remaining frames. Because of the synthesis process, occasionally there can be artifacts based on the content of the application. So we're working hard to reduce those artifacts. One of the most obvious artifacts is when objects move very quickly. They can sometimes show this like sawtooth effect. The cause of this sawtooth is when the object moves really quickly, the foreground hand and the background can overlap. And because our compositor doesn't actually take into consideration the order of these objects, it can kind of render them in random order, which can lead to this weird effect. So there's a very simple way we can fix this. We can simply enable depth testing in the compositor, which almost completely resolves this artifact, as you can see in the below image. So this does add a small amount of GPU overhead. However, we think you're going to love the quality difference and make this trade-off totally worth it. You can test this out today using this ADB command. So while this is a great improvement in quality, it doesn't completely eliminate the artifacts you might see with application SpaceWarp on fast movement. As you can see in the below image, you get kind of a weird warbling effect on the edge of the hand. So I've kind of gone back to the drawing board a little bit with application SpaceWarp to try to remove this artifact. And what I've come up with, I'm calling adaptive mesh application SpaceWarp. And essentially, this new technique considers the content of your scene when generating the mesh used by the compositor to try to wrap the foreground object so that it stays cohesive and together. Even under high movement, it won't show any kind of warbling effect. You can test out this new technique today using this ADB command. Additionally, we're going to begin rolling this out to developers and users over the next couple months. The next topic I'm going to talk about today is GPU tile alignment. As many of you know, the MetaQuest family of devices use tile-based GPUs, which is a great win on our mobile hardware. Because we can divide the scene up into a number of tiles and render them individually, you can throughput a lot more pixels on our hardware. So this has a lot of advantages, but it does have one side effect in that it adds an extra step as part of the rendering, which is called binning, where we assign each triangle of your geometry to a specific bin or a specific tile. And that means as the number of tiles increases, the GPU time also increases. So while you may expect that the performance curve looks something like this, where as you increase render scale and thus the number of pixels, you would expect the GPU time to scale linearly with the number of pixels that you're rendering. However, this isn't accurate for our device. A more realistic curve for our device is something like this. The GPU tile time scales linearly with both the number of pixels and the number of tiles. So as your resolution rolls over to the next number of tiles, you'll see this stair-step effect in the GPU performance. So what does this mean? A small render scale change can have large performance implications. We've seen that by dropping resolution in some cases about 1 or 2%, you can actually get up to a 5% GPU performance increase. Additionally, because our fixed foveated rendering technique is tile-based, it's possible that at some resolutions, increasing a small amount can actually drop the number of tiles that your application is rendering, which improves performance. So, how do you take advantage of this information? The first option, which is what we would recommend to pretty much every developer, is to turn on dynamic resolution. Because we take into consideration the tile sizing, we can recommend a resolution for your application to render at that is going to give you the most GPU performance per pixel that we can possibly give you. However, not everybody's going to turn that on, so if you're not going to, for whatever reason, you should be very careful about the resolution scale that you're selecting for your application. We recommend reevaluating the resolution scale you've selected by incrementing and by 0.01 or so up and down a couple of steps and measure the performance at each one. You'll likely find one of those scales will give you a more optimal GPU performance profile. To do this kind of analysis of taking GPU timing measurements, we recommend using OVR GPU Profiler. To get the most accurate total frame time, we recommend using low overhead mode, which eliminates a lot of the overhead when taking specific render stage sampling. Additionally, if you're trying to get accurate application timing, we recommend pausing the compositor when you're taking these measurements to avoid preemption, which can blow up your GPU time more than it actually takes. The next topic I'm going to talk about is symmetric projection. Symmetric projection is a feature that can be enabled for Vulkan apps in Unity and Unreal Engine. And because of our hardware, if the application renders both eyes with the same field of view, there is a significant speed up. However, the field of view for each eye on our devices is actually quite asymmetric. You can see much more on the outside of your field of view than the inside. So, to create a symmetric field of view, we basically merge the two, create a much larger field of view, which also means we have to render a lot more pixels. However, we can use our fixed foveated rendering technique to actually just turn off the inner invisible pixels. And so overall, this ends up being a pretty good GPU win. We've made a couple of changes recently to the symmetric projection implementation in the Oculus XR plugin for Unity. We've improved the field of view calculation to ensure that both eyes use exactly the same field of view for optimal GPU performance. Additionally, we've adjusted the way that we calculate the resolution used when using symmetric projection so that it matches the aspect ratio more closely with the actual field of view, so that you avoid any kind of stretching of pixels when it's sampled in the compositor. We find both of these small changes do add up to a very small performance win in most applications. So we recommend updating your Oculus XR plugin to get these changes. So the last thing I want to talk to you about today is subsampled layout. What is subsampled layout? Well, if you're using our fixed foveated rendering, essentially in the periphery, the tiles are rendered at a smaller scale than the full eye buffer. Normally, we would have to then upscale this low resolution image so that it fills the whole image buffer. But with subsampled layout, we can actually leave it at the resolution that it was originally rendered at. And then in the compositor, we can sample from this lower resolution image. This saves us a good amount of performance in the memory bandwidth required to copy from GPU memory to main memory. Additionally, it has a side effect that is kind of a nice bonus, which is it reduces aliasing in the final image in the compositor. On the left, with the original upscaled version, you can kind of see the pixel blocks in the image, whereas on the right, these pixel blocks are nicely bilinearly filtered so that you get a nice, smooth appearance. We recommend that pretty much every developer should use both subsampled layout and symmetric projection. However, there is a case today where these don't completely work, which is if you're using post-processing or any kind of intermediate pass in Unity, this step will only be applied to the final pass, so you may actually get a performance decrease. We're working with Unity actively to make sure that both of these effects are applied to every step of your rendering pipeline so they become a pure win, and we can universally recommend that you use them. So I'm going to hand it back to Neil, and he's going to share some updates on a few more areas we're working on to up-level quality and improve performance.
Thanks for the great overview, Trevor. Some of the things we're most excited about there are not just the bevy of CPU and GPU wins that you just shared, but maybe most importantly is that step function win in SpaceWarp that you were able to achieve with that pretty novel algorithm. Being entirely transparent. So a few years ago, we shipped SpaceWarp to quite a lot of dev and maybe even community excitement. Everyone hears that number, 70% more CPU and GPU, and of course we're all going to get excited. But truthfully, at the same time, if there's one dev complaint that we've heard over and over again with SpaceWarp, it's been that the artifacts have sometimes been a little bit too much to handle. And that's what Trevor has essentially done, take direct aim at what we think are the two most strongest AppSW artifacts, and we've been able to almost mitigate them. So really excited to see which of your dev apps are now going to use SpaceWarp, which maybe had previously concluded that the artifacts were a little bit too much to handle. I'm going to follow a pretty similar blueprint to Trevor's section, both talking about some pretty massive visual quality wins that we're able to achieve, as well as some GPU and CPU perf improvements that each of which should give your apps a multi-FPS win. Here's the agenda of what I'm going to cover today. First things first, a GPU frequency boost. This one's pretty linear, pretty simple. You might have heard it in one of the keynotes earlier today. You're just going to get a higher frequency to render at, which is almost always a good thing. Then we're going to discuss the Vulkan subpass system, which has existed for a long time in our Unreal Engine integrations, and we've seen some really cool use cases like tone mappers, and we're really excited about being able to share the same functionality with Unity now, as well as some cool new rendering effects that have come out of that. After that, we're going to switch gears and talk about a somewhat new rendering architecture named Forward Plus. I can almost guarantee that virtually every one of your apps in the audience uses forward rendering today. And we're going to discuss why Forward Plus may be the right call for some of you devs, but definitely not all. And finally, we're going to talk about a pretty large win that we were able to achieve for Unity CPU performance by improving the Unity feature named graphics jobs, which led to a pretty serious FPS win in some of our top content already. So first, let's talk about the GPU frequency boost. If you remember from last year's Connect, these were the Quest 3 launch frequencies. And there's a lot of numbers here, but the one thing to conclude is that the device is over 2x faster in floating point calculations performance compared to its predecessor, the Quest 2. And we're really excited to see how over the last 12 months, a lot of you apps have utilized this to its fullest extent. Maybe the simplest way to utilize that is just bump up the render scale. That's the easiest. A lot of you devs probably did that in day one. But then you started looking at mesh changes, shader changes, material changes, maybe adding a few post effects. So we were really excited to see how all of these rolled in the last 12 months. And to be clear, we worked pretty hard exposing almost as high of a GPU frequency as we could back then. We really left no stone unturned because the more compute we can give, the better. But it turns out that there might be a little bit of spare headroom for a few view apps. Not all of them. It's extremely dynamic. But the idea is essentially that the available headroom in the device is going to inherently be workload specific. Because every workload is different. Based on your shaders, you're going to push different amounts of memory bandwidth. Memory bandwidth essentially being the amount of texture memory or uniform buffer memory that your shaders are reading. Different meshes are going to subject the GPU to sort of different constraints. So the idea is when you put this all together, the thermal requirements of your apps all differ one from another. And that's why our challenge is essentially now, how do we design a system that works well with everyone, but that maybe most importantly can provide a little bit of a visual quality boost to those remaining apps that had a little more thermal headroom left. And that's why we're really excited to say that we've been able to ship up to 10% higher of a GPU frequency by enabling a dynamic system. So we're happy to say that we've been able to further boost these GPU frequencies up from what we shipped at the Quest 3 launch a year ago by up to 10%, but only when the feature dynamic res is enabled. So why are we tying it to dynamic res? I can promise you that the reason isn't just that we want to force you guys to use an arbitrary Meta Quest system feature that we've devised. But simply put, we need a way to be able to scale up your GPU utilization, your visual quality, whenever there's that a little bit of thermal headroom available. But sometimes the thermal headroom isn't there. We also need to be able to scale it down or not scale it up in the first place. And a dynamic system like dynamic res, it has a bunch of benefits, some of which are what Trevor just cited. It can select the optimal tile-aligned resolution, but it can also allow you to scale up and consume that thermal headroom or not eat into it whenever you don't want to eat into it. And why are we claiming up to 10%? Well, simply put, because this is thermally dependent, the benefits are going to be inherently dynamic. If you don't have that thermal headroom, you're not going to be able to be boosted. But we think for most of you apps, you will have that little bit of thermal headroom available. So we think a lot of you apps will get the upper end of this range. And as a really cool data point, right after we ship this, one of our top graphics apps, Red Matter 2, which is already known for really good graphics even before an experiment like this, they were able to sustain the upper end of this frequency, which is all the way up to 640 megahertz GPU frequency, because they had already enabled dynamic res. And therefore, when we landed this a couple months ago, they just got the win for free. They were able to sustain the 10% more GPU frequency for up to 85% of all frames. So that's a really good signal that we do have a little bit of thermal headroom that's going to help all of your apps as well. So if there's one takeaway from this section, it's that we're enabling a lot more GPU, but you're going to have to enable dynamic res to get it, because there's some really good reasons why we're tying these together. Definitely let us know any questions or pain points along the way of the Unity and Unreal integration of dynamic res. So next we're going to talk a little bit about the Vulkan subpass system, and most importantly, the series of graphics effects, both post-processing as well as some interesting transparency rendering effects that are now enabled by the Vulkan subpass system. And we've been hard at work at all layers of the stack, starting with Qualcomm, who's done a lot of good work at the graphics driver layer, shipping a few new Vulkan extensions for this. And we've integrated these to the shader level in Unity and Unreal so that your apps can benefit really with some simple built-ins. Now, we've talked about Vulkan subpasses a little bit in the past, but here's a pretty interesting visual, because a picture is usually worth 1,000 words. So there's a lot going on in this image, but what this essentially is just a mental model of something like a tone mapper. Just a very simple standard post-processing effect. The idea is essentially that you're doing your normal render pass. You're doing forward rendering, let's say, might have like 500 draw calls in there, whatever standard scene setup that you have. Then, once you're done with that, you have to write that out to system memory. But to do the post-processing effect, the reason this is so expensive in our hardware is that you have to read it back. That's really costly, because to even be able to sample from that texture and then do something with it, combine it with a color lookup table or whatever else you might want to do, you first have to move it from system memory, which is where it lives after it's been rendered, back to GPU memory. And if there's one thing to take away from this image, which is the status quo essentially, it's that there are 3 of these arrows. And each of the arrows is a really expensive memory bandwidth transfer, which is one of the most expensive operations on our Qualcomm hardware, both from a battery life and thermal perspective, as well as from a latency perspective. So you want to minimize these arrows, these memory bandwidth transfers, as much as possible. So now let's look at what happens when the Vulkan subpass system is enabled. You'll notice that there's only one of these arrows, which is a little bit stunning because the rendered image is virtually identical. You still have a tone mapper. But now you can keep all that color data still in GPU memory after you've rendered it. You do your main forward pass, which all of your apps already have today, keep the data there, just do the tone map right on top of it, sort of an in-place operation. And once you're done with it, you just write the output to system memory. So this is particularly useful for a couple different post-processing effects. Specifically, a few would be tone mapping, color grading, and HDR. We want a disclaimer, which is to say that we didn't just give you like fast boom. This isn't going to scale to every single post effects, but a bunch of them are now going to be quite a bit faster. And we're excited to say that we spent a lot of time making the Unity integration pretty good here. Now, Vulkan subpasses are not just a win for the post-processing effects like tone mapping that we just outlined. We went back to the drawing board the last few months, and we're pretty excited to say that we found one use case that was a lot stronger than probably what we previously thought. And we think there are a bunch of dev art use cases that can come out of that. And that's what we're calling, it's something that we're calling in-place depth lookup. The idea is that in all of your transparency shaders today, you're almost definitely not accessing depth, because to access depth in our mobile hardware, it was going to be prohibitively expensive, essentially in that memory bandwidth. On other platforms, you might be used to having depth in that transparency material, but on our platform, you've never been able to have it. But with the Vulkan subpass system, pretty similar to the previous point about tone mapping, the data is already there in GPU memory. You can just sort of piggyback off of it, really just sample from the depth buffer already there, write out your transparency effect, and then you only have one of these expensive arrows of the memory bandwidth transfer again. So notice how there's no memory round trips to enable this. There would have been without using the Vulkan subpass system. And the proof is always going to be in the pudding for effects like this. We're not just saying that we were able to give you a vague graphics effect, but we're really excited to say that in our upcoming 1P title, Batman Arkham Shadow, they were able to use it for a slew of transparency rendering effects, two of which are shown here. So these are water rendering effects. What you really want to focus on here is that when the water intersects these beams in both images, there's a little bit of a blend, a fall-off effect. And the way this is rendered is that in the water transparency shader, in that material, it's able to sample from the depth that was already there. In this case, the depth is written by the beam. And once you have access to depth, you can essentially render this fall-off, this blend effect. And there's a bunch more you can do, not just limited to effects like this. Soft particles are a great example. A lot of you devs have probably known that you can't just do performance soft particles in our platform, but here, the depth is right there. It should be pretty doable now. And there's a lot more use cases that we're really excited to see what you're going to do with it. Now, there is one caveat with the Vulkan subpass system. It's entirely piped end-to-end through Unreal. It's working pretty well on the Unity end, and that's why in the next few days we're really excited to ship a URP fork version that's going to enable these. And we're also hard at work upstreaming this to Unity's mainline URP. We don't want to have to subject all of you devs to just grab our fork, but the mainline upstream is always going to take longer. So for now, you're going to have access to it in a fork. And there's one or two engine PRs that still need to land in the Unity side. They have not landed yet. That are going to essentially pack on a few percent GPU win for Vulkan subpasses. So takeaway here is that there's a bevy of post effects that you've never been able to achieve pretty performantly in our platform. And they're now finally here for Unity, and they've been here for Unreal for a decent while now. So we're excited to see what you can do with it. Now we're going to talk about another possibly foundational graphics feature which could transform your visual quality. And it's known as forward plus rendering, which we've spent a little bit of time in the last few months really productionizing inside of Unity. So the main pain point that really started a lot of this work is that you MetaQuest devs can't really use many dynamic lights in a traditional forward rendering setup. You might be familiar with curves that somewhat look like this. Essentially, as the number of dynamic lights really scales up, your app GPU time is going to scale with it somewhat linearly, and that's just an artifact of the way forward rendering works. And that's why the number of dynamic lights in, I can guess, virtually all of your apps has probably been in the low single-digit count, maybe somewhere like 4 or 5, give or take. Now, enter forward plus to provide an interesting spin, an interesting new algorithm for how this can scale significantly better. The way forward plus essentially works is that it divides your scene into a set of tiles, also known as clusters, and you only have to perform lighting calculations really on a per cluster basis by considering what lights affect that cluster. So maybe a good mental model is that if you have 100 dynamic lights, per cluster, there aren't going to be 100 dynamic lights that affect that cluster. 100 dynamic lights are going to affect your entire scene, but maybe only 5 dynamic lights affect a given one cluster. So you're only going to pay this lighting cost for those 5 dynamic lights on that per cluster basis. And that's why we see this scaling law, the graph that's visualized here, which is that at a much higher number of dynamic lights, forward plus rendering is going to blow forward out of the water. But there's also an interesting caveat, which is that at a lower number of dynamic lights, forward rendering is pretty much going to win all day. And that's why you probably don't just want to willy-nilly just enable this feature and assume it's going to be a perf win. It really depends on your art style. It depends on how many dynamic lights that your tech artists probably want to enable. So the devil really is going to be in the details here. It might even depend on your object size because there's some nuances there, not just your light count. Now, this is an interesting little heat map visualizer where you can essentially see that red means a bunch of different lights are touching a given cluster, and green means that not that many lights are touching that cluster. And the idea of forward plus is essentially trying to distribute all these dynamic lights pretty well through the scene so that you can have as fewer red tiles as possible. Obviously, the more green, the better. Now, if there's one takeaway from the forward plus piece, it's that it's not something to blanket turn on, but we have heard from some of your art teams that you want to have this flexible look. You want to be able to just pepper in dozens of dynamic lights. If that's you, maybe you should give forward plus a try, because before our recent changes, it was prohibitively expensive in Unity. Like turning it on in Unity would essentially have doubled your frame time, and now we're able to see the pretty powerful scaling that we showed in the previous graph. Now, we've discussed a pretty long laundry list of GPU improvements, and to be very clear, we don't want to neglect CPU. It's almost like right at the top of our list, right there next to GPU in terms of what we want to optimize. Maybe there's a few more opportunities for GPU because there's so many unique things about XR, the way Trevor just shared, subsampled layout and symmetric FOV. So there are a lot of opportunities for GPU, but whenever we see CPU opportunities, we also want to pounce on optimizing away those. And that brings us to where your CPU apps are typically bounded by. And from what we've seen is that when you're CPU bound, the bottleneck is often going to be the main thread. Now, what is the main thread doing in general? A lot of it is serving a pretty good purpose. The main point of the main thread in any game engine, especially an engine like Unity, is essentially to do simulation, to do physics simulation, animation, etc., to really move all your objects from frame to frame. And even though most of that is essential, we found a couple of interesting optimization opportunities when taking a closer look. So notice how in this visualized image here, there's a little bit of rendering work on this main thread, which is almost oxymoronic. We know that a render thread exists, so why is there quite a bit of rendering work that's occurring in this main thread in the first place? Can we move it off that main thread? Now, Unity utilized this too, which is why they were able to ship a feature named graphics jobs, which does a couple of things. The first thing the graphics jobs does is move this rendering work off of the main thread, which is really, really good. And that's why a lot of our devs have actually been able to utilize graphics jobs. I'm sure some of you are familiar with it. I know the Barbaria devs in the audience were able to utilize it for some great CPU wins. But then we started to look a little bit deeper at the feature, and we found that there were some really unintended consequences, which probably led to more problems, more harm than maybe good in the first place. And that is that it was trying to multi-thread the render thread, but coming with some serious consequences. So why is multi-threading the render thread bad? You're probably thinking as a mental model that might be a good thing. If your render thread was 9 milliseconds, you multi-threaded it across 3 parallel threads. Shouldn't it be 3, 3, 3? Haven't you just divided your render thread time and latency by a factor of 3? And in an ideal world, the answer would be yes, except for an implementation detail, really a quirk, a hardware quirk, which is based on the implementation of multi-threading the render thread on our hardware. They use a feature known as Vulkan secondary command buffers, which is essentially how this command buffer recording process, which is what the goal of a render thread always is. It's to record command buffers, which tells the GPU what to draw. When you try and use secondary command buffers to record these in multiple threads, this unfortunately comes with a GPU perf regression, which is just really unavoidable in our hardware, somewhere in the order of 4%. So that's obviously not good, but thankfully we were able to have our cake and eat it too. We realized that a low-hanging fruit win would be keep the main thread offloading benefits of graphics jobs, but just stop multi-threading the render thread. We don't want to give all your apps that 4% GPU win. So that was a pretty simple fix, but we're happy to be able to have landed it because now your dev teams don't need to be faced with that trade-off of whether you can turn on this really cool CPU feature, but have to sacrifice some GPU as a result. But we weren't done there yet. Because after studying both Batman Arkham Shadow as well as some more CPU workloads of a lot of our top Unity apps, we realized that there were one or two more future improvements that we could make. And they're found essentially in this image. Notice how in this image, you're actually still seeing some rendering work done in the main thread up top. We really want it to be done on a worker thread, which is one of those bottom two threads, but it's not done there. And essentially the reason is that in these outlier but still significant scenarios, the main thread was actually acquiring and executing these jobs, which definitely sounds a little bit ironic since we just told you that the entire purpose of graphics jobs is to move work off of the main thread and to allow that main thread to then proceed ahead with everything else, which essentially is simulation for the next frame. That's how you increase the main thread throughput. You just offload it. But it's not doing that here. So could we prevent that? And thankfully we could. So in close collaboration with Unity, we've been adding a functionality that we call no main thread stealing to the graphics jobs feature. The idea is pretty simple. We realized that we want to offload the main thread by any means so that it can move on to frame n+1, while these job worker threads are still doing graphics jobs for frame n at any given time. And we're really excited to say that this feature, or this particular improvement, led to an additional win of 2 FPS in our upcoming 1P title, Batman Arkham Shadow. Now, we almost buried the lead with how big of a win the graphics jobs is overall, because after combining all the wins that we just talked about, both this 2 FPS win, as well as the 4% GPU win by not multi-threading the render thread, we're excited to say that, that Batman Arkham Shadow saw an up to 21% FPS win in their entire content by enabling graphics jobs. So if you're a Unity dev, thanks, yeah. You don't see 21 every day, so I'm really glad we started clapping because 1, 2, 3, that's sort of in the arena that we operate in. But 21 just shows it's almost a testament to how crucial your Unity main thread perf really even is. It's where your C# executions mostly lie on. Unless you're doing a lot of like job system work, which is definitely a great idea, but optimizing that however we can is always a good idea. One caveat we have to say is that we're landing these engine wins with Unity right now, because these are pretty deep engine changes inside Unity's core Vulkan renderer. They're in the process of landing right now, and we're really excited to land them to a slew of Unity versions, definitely Unity 6, and we're still evaluating other versions soon. So there you have it. We've talked about a few key pillars today. It really starts and ends with GPU perf, our optimization journey, as we said. But CPU perf is nothing to sneeze at, and we've been excited to make a few key visual quality enhancements, which Trevor really kicked things off with by describing that step function win that we've made to app SpaceWarp. And we know a lot of you devs definitely were maybe pumped about that 70% budget win that you get with app SpaceWarp, but maybe you tried out the feature and then you concluded that the artifacts were a little bit too much to handle. So if that's you, maybe your homework right now is give it another try and see if it's ready for your content now. And then we cover just that slew, that long tail of almost a dozen different CPU and GPU wins, whether it be subsampled layout, symmetric FOV, graphics jobs, Vulkan subpasses, and forward plus rendering. Not all of these are going to be applicable to you, but we really think that most of them are. And the best part about it is that almost all of them are independent of one another. Each one of them is basically like a few percent FPS win, or a CPU utilization or GPU utilization win in and of themselves, and then they stack up to almost definitely be a double-digit FPS win for every one of your apps. So remember, whenever we expose more perf like this, it's only really going to be that useful if you devs can then use the larger budget to do something more. Otherwise, all we're really doing for you is like a measly battery life win, if you think about it. When we make perf wins, the ball's in your court to then render that one more avatar, or maybe rework your physics system to give users a lot cooler of an experience. So it's pretty simple, devs. It's up to you to use these wins and add a lot more cool content. So thanks everyone for your time.